In this video, we're going to learn about parameter initialization strategies that you can use to initialize different layers in convolutional neural networks. So let's dive right in. Parameter initialization strategies. Thus far in the previous videos, we discussed why it is important to use transfer learning, where you initialize parts of the network with pre-trained weights from training on large datasets such as ImageNet. But how can we initialize the other layers in our architecture that were not a part of this network that was used for pre-training? Or how do we initialize the layers of the network during the pre-training stage in the first place? That's what we're going to be discussing in this video. So for optimization with gradient descent, it actually matters a lot where you start. So initializing all the weights to 0 leads to the neurons learning the same features during training. Whereas initializing the weight values either too small or too large leads to either slowing the learning or diverging. Therefore, choosing proper values for initialization is necessary for efficient training. So let's look at an example here. So in this visualization, if you start basically here, then you start going this way down. But if you start, let's say over here, then you're going to go this way basically. So the starting point can actually affect the convergence of the method and the minimal cost that's found in the end, and the generalization error as well. So therefore, the parameter initialization strategies are a current research topic. However, so far, typically what's mostly used is relatively simple heuristics. Importantly, you should always take care to initialize the weights to break symmetries. For example, the weights of multiple hidden units in the same layer should be initialized differently from each other, because if you were to initialize the inputs and the output weights of two units to the same values, then the two would remain the same. So for the forward pass would make the same computation for both of them, and you would get the same activations in return. Whereas in the backward pass, you would compute the same gradients, and then the same update steps would make the same updates. And the two weights would never get different values. So rather what you want to do is that we would like to try to initialize the weights for units to compute maximally different functions. In practice, typically the weights are just sampled randomly from a distribution. And now the question is just which distribution to sample from. And the biases are typically initialized to a constant. So there's also more advanced initialization methods such as self-supervised learning or transfer learning by pre-training on large data sets that we discussed, or even meta learning across different data sets to decide what a good initialization would be. And so here we will discuss now standard heuristics for initializing the weights and for initializing the biases as well. And we'll very briefly look at what these more advanced methods also do. So let's first look at how to initialize the weights. We typically sample these weights from a distribution, typically a uniform distribution or a normal distribution, and the scale of the distribution is quite important. If you would like to break symmetry, you would like to have some large weights and to make sure that there are activations flowing in the forward pass and you don't get zero activations. Then you would like to have large weights. But in order to avoid exploding gradients and in order to get good generalization, you would like to actually have a small scale of your weights. So these are different types of forces pulling large or small, and it really is an empirical question at the end of the day, how large you would like to choose the scales of the uniform or normal distribution. One distribution that's become very popular is called as the Xavier initialization. And this is from a paper by Xavier Gorlot and Joshua Bengio. This Xavier initialization sets the lower and the upper bounds of the uniform distribution as a function of the number of inputs m and the number of outputs n of a layer. And this is in order to compute the compromise between two goals. namely initializing all the layers to have the same activation variance. So for that, the number of inputs is important, and the same gradient variance. For that, the number of outputs is important. In practice, the scale of these weights, so the 6 year, is definitely a layer-dependent hyperparameter that you can tune. Another approach that one could follow is to actually preserve the norm of the activations and of the gradient when propagated through the network by trying this out on a few mini batches. And this is actually something that can be done based on some initial trials on a few mini batches. You can push a few mini batches through the network and see if the norm of the activations in the first layer is kind of similar to those in the middle layer and the last layer, or if there are these large differences. And you can also likewise compute gradients and see if the gradients are vastly different for different layers. And if they are very different, then you can adjust the initialization bounds to make them this less different in order to basically ultimately make it easier to come up with the learning rates that work relatively well for the different layers. All right, so for the biases, we initialize them typically as a constant. Often we actually just use 0, except for some example output units. You typically set the bias vector to match the desired output statistics. So if you have a classification problem that's imbalanced and you have class proportions C sub of I for each class I, then you would actually set the bias vector such that if you apply a softmax to just the biases, you actually get this class distribution out. And that can be very helpful if you only have, for example, 5% positive data and 95% negative data. So in order to avoid gradient descent having to learn this from scratch, so this is why we do it. So you simply initialize the biases, and then gradient descent will already start in the right regime where you have about right proportion of positive predictions and negative predictions. So another exception are ReLU units. So there we don't typically initialize the biases to 0 in order to avoid saturation, because we want the ReLUs to often be in the positive range in order to avoid the so-called dying ReLU problem. And here the activations become smaller than 0, and then, well, it's as if the unit is basically dead. If the activations are 0 for all the different inputs, then the unit just doesn't matter anymore. And it could as well be dropped and the computation could be saved. So typically you want small positive bias such as 0.1 in order to avoid the ReLU from dying. There are also some other examples. So if you have gating units, then you typically initialize the biases close to 1 in order to open the gate. One prominent example of this is in LSTMs, where you typically initialize the bias of the forget gate to 1. All right, so in the final set of initialization strategies that we will discuss, warm starting and meta learning. Both of these make use of different data sets in order to come up with good initializations. Warm starting means that you initialize with the results of a previous optimization on a different task. So this is basically the transfer learning that we just discussed before. So one example of this, as we discussed, can be the NLP task where we predict the next word in the sentence, or in the case of images where it can be predicting, for example, rotations or jigsaw and so on. So here we basically given a data set with labels, which is typically much smaller. You start your optimization from the pre-trained weights and just fine tune with relatively small learning rates to not unlearn too much of the pre-trained representations. So this is exactly what we just saw before. And this process basically allows you to train large neural networks on small amounts of label data without overfitting, and by reusing large parts of the learned representations and only using a small learning rate, not to unlearn too much of the learned representations. So finally, what meta-learning good initialization does is to look across different data sets for initialization of weights that would perform well. For example, this MAML approach here, which stands for model agnostic meta-learning, actually uses a second order optimization process that computes the losses you would obtain on several data sets if started with the current initialization, and then combines these losses to form a meta gradient by which it updates the initialization. And this is in a way that it will yield better results for SGD for the individual data sets. And if you're taking the AutoML lecture, you will learn more about these meta learning approaches in detail. All right, so this brings us to the end of this video, and I have two questions for you. Why would you want to preserve the norm of the activations and gradients when propagated through the network? And can you think of some examples of tasks that could be used to perform transfer learning for each other? With that, I encourage you to pause this video now and to try to answer these questions, and I will see you in the next video. Thank you.